Welcome to the new era of video creation with Baozi. This is our new series on teaching deep learning. Today, we will discuss the key point detection and matching. Here are the contents. In computer vision, key points are distinctive points in an image that can be reliably detected and tracked across different views or images. These key points typically represent interesting structures like corners, edges, and blobs in an image, and they are used as anchors for many vision tasks. Key point detection refers to the process of identifying these points in a given image. Once detected, these key points can be matched between different images to recognize objects, perform image stitching, or track the motion of objects between frames. Key point matching refers to finding the corresponding key points between two or more images. This is a fundamental task in applications such as 3D reconstruction, panorama creation, and object recognition. The ability to match key points across images is what allows systems to understand relationships between different perspectives of the same scene. Key points are important in computer vision because they are invariant to certain transformations. For example, they can remain unchanged when the image is rotated, scaled, or slightly modified by illumination changes. This invariance is crucial for reliably detecting and matching key points across different images of the same scene or object. The use of key points also simplifies the process of image matching. Rather than comparing entire images pixel by pixel, which is computationally expensive, key point-based methods allow us to focus on a small set of distinctive features, reducing computational complexity. Additionally, key points are valuable for dealing with challenges like partial occlusion or cluttered environments. Even if parts of the image are hidden or obscured, as long as key points are detected in the visible areas, matching and recognition can still occur. There are several key point detection algorithms that have been developed over the years. These algorithms are designed to find points in an image that are stable under various transformations, such as scaling, rotation, and changes in illumination. Some popular key point detection methods include Harris corner detector. This is a classic method that identifies corners in an image by analyzing image gradients. It computes the second moment matrix of gradients and looks for points where the eigenvalues indicate a corner, high curvature in two directions. SIFT, scale invariant feature transform. SIFT detects key points across multiple scales, making it robust to changes in scale. It works by identifying regions of interest, key points, in an image, and describing their local image structure using orientation and scale invariant descriptors. These features are highly distinctive and can be used for matching key points between images. SURF speeded up robust features. SURF is a faster alternative to SIFT. It uses a similar approach but approximates the computation of image gradients and Hessian matrix to speed up the detection process, making it more efficient while maintaining robustness. ORB, oriented fast and rotated brief. ORB is an efficient algorithm that combines the fast corner detector and brief descriptor. ORB is particularly useful for real-time applications due to its speed, and it also provides robustness to rotation. Once key points are detected, it is important to describe the local image patches around these points. The key point descriptor is a vector that characterizes the local region around a key point in a way that is invariant to transformations. SIFT descriptors. The SIFT descriptor uses a histogram of gradient orientations in a local patch around the key point. It captures the unique texture of the region surrounding the key point, making it robust to rotation, scaling, and slight changes in illumination. SURF descriptors. SURF uses HAR wavelets to compute a fast and robust description of the key point's local neighborhood. These descriptors are efficient and suitable for real-time applications. Brief. Brief is a binary descriptor that represents local image patches as binary strings. It is faster than SIFT and SURF due to its simplicity, but it requires efficient matching algorithms to handle large datasets. Freak. Freak is inspired by the human visual system and uses a series of binary tests on image patches, similar to Brief but optimized for higher accuracy. It is computationally efficient and can be used for real-time applications. Once key points and their corresponding descriptors are computed, the next step is key point matching, where we find corresponding points between different images. This is achieved by comparing the descriptors of detected key points in one image with those in another image. Brute force matching. The simplest approach to matching key points is by comparing all pairs of descriptors between two images and selecting the closest ones. This can be slow for large datasets, so other methods are often used to speed it up. FLAN, fast library for approximate nearest neighbors. FLAN is an optimized library for finding approximate nearest neighbors efficiently. It reduces the time complexity of matching, making it suitable for large datasets and real-time applications. Ratio test. To reduce the number of false positives, a ratio test is often applied. This test compares the distance of the nearest neighbor to the second nearest neighbor, keeping only the matches where the nearest neighbor is significantly closer. RANSAC, random sample consensus. RANSAC is a robust algorithm that helps eliminate outliers. When matching key points, some correspondences may be incorrect due to noise or mismatches. RANSAC helps by iteratively selecting a subset of matches to compute a transformation model and rejecting outliers based on this model. Keypoint detection and matching are widely used across various computer vision tasks. Object recognition. Keypoint matching is used to recognize objects by finding corresponding key points in images of the object from different viewpoints. The object is identified by matching key points between the query image and reference images in a database. Image stitching. Keypoint matching is crucial for image stitching, where multiple images are combined to create a panoramic image. By finding and matching key points between the overlapping regions of two images, we can align them and blend them together seamlessly. 3D reconstruction. In applications like structure from motion, SFM, keypoint matching is used to reconstruct 3D scenes by finding correspondences between key points in multiple images and estimating the scene's geometry. Augmented reality, AR. In AR, keypoint detection and matching are used to track real-world objects and align virtual content. By detecting key points in the camera feed, AR systems can anchor digital objects onto real-world surfaces. Despite their importance, keypoint detection and matching come with several challenges. Scale variation. When the object is viewed at different scales, key points may become harder to detect or may appear at different locations. This is particularly problematic when there are significant differences in the size of the object across images. Rotation. Objects or scenes that are rotated may cause the key points to change their orientation, making matching difficult if the algorithm does not account for rotation. Occlusions. When part of the object or scene is hidden in one image, key points may be missing or difficult to match. This can happen due to objects moving in or out of view, or when parts of an object are obscured. Lighting changes. Changes in lighting conditions can affect the appearance of key points, especially when using image descriptors like SIFT or SURF, which rely on intensity-based features. This can lead to mismatches or missed key points under different illumination. To address the challenges of key point matching, several strategies can be employed. Using multiple descriptors. Combining multiple descriptors, such as using both SIFT and brief, can improve the robustness of matching under various conditions. Keypoint localization. Improving the localization of key points can help reduce errors in matching. Key points should be detected at locations with high precision and stability. Multi-view geometry. When working with multiple images, using geometric constraints like epipolar geometry or triangulation can improve the accuracy and reliability of key point matching. Learning-based approaches. Recent advances in deep learning have enabled the training of models to directly learn key point matching, improving robustness in challenging scenarios, such as occlusions or lighting changes. Real-time key point matching is crucial for applications like augmented reality, robotics, and autonomous driving, where fast and accurate feature matching is needed to ensure smooth and responsive systems. Efficient algorithms, such as FLAN and approximations of nearest neighbor searches, are critical for speed. Using hardware acceleration, e.g. GPUs, can further speed up matching processes. In real-time systems, optimization techniques, including downsampling and approximation methods, are often employed to strike a balance between computational speed and matching accuracy. The future of keypoint detection and matching is exciting, with new developments in deep learning and multimodal sensor fusion. Recent work explores using deep neural networks, CNNs, to automatically detect and describe keypoints, which could improve robustness and accuracy compared to traditional methods. These deep learning models can learn features directly from data, potentially removing the need for handcrafted descriptors. End-to-end systems are becoming more common, where keypoint detection and matching are integrated into a single pipeline that can be optimized jointly for accuracy and efficiency. As more multimodal sensors become available, we can expect to see multimodal matching techniques that fuse information from visual sensors, depth cameras, and other sources to improve matching accuracy and robustness in real-world applications. In conclusion, keypoint detection and matching are pivotal in many computer vision applications, from object recognition to 3D reconstruction and augmented reality. While significant progress has been made with algorithms like SIFT, SURF, and ORB, challenges like scale variation, occlusion, and lighting changes remain. Future developments in deep learning and multimodal sensing will continue to push the boundaries of keypoint-based methods, making them more robust and efficient for real-world applications.